Welcome back. Puzzle time, folks. Puzzle time. I'm excited. Here's what we're going to do. We are going to take this circuit. This handout is available to you again in that All Resources folder if you get a chance to print it. It'll save you a bunch of drawing. We're going to get into these puzzles where we are looking at this circuit right there. And our end goal is to figure out how much voltage do we spend at every single resistor and how much current is going through every single resistor. Now, in order to do that, we need to follow a series of steps, and it's always these three steps. So step number one, we need to first find the total resistance. Once we find the total resistance, we will quickly find the total current. And then once we have the total current, we head to our physics electricity toolbox. We use Kirchoffs laws, junctions and loops, and Ohm's law, and we start finding all the individual voltage drops and currents. So let's look at just that first circuit there. We need to find the total resistance. So what I want you to do is look at that circuit and ask yourself, are there two resistors that are maybe in series, or do we have two resistors maybe that are sitting in parallel? And if you stare at that for a minute, you might recognize that resistors 3 and 4, right there, are sitting side by side. They have only wire connecting their tops. They have only wire connecting their bottoms. They are in parallel. So what I would suggest when you're going through and doing the actual calculations with this is to make little notes for yourself, because it's really easy to sort of forget and lose your train of thought. And if you don't put little notes for yourself and there's just random numbers all over the page, you're going to look back at it. I might look back at it. A friend might look back at it and have no idea what was going on. So parallel. What I'm going to do is I'm going to combine resistors 3 and 4 into resistor 5. It's imaginary. It doesn't actually exist, but we're going to take the two of them and sort of squish them together into one. And I'm just going to go with the next number in the number line. And I'm going to call it resistor 5. I should technically be calling it 1 over resistor 5 because that's what the math says, but I'm just going to take care of it on the calculator. Remember, with parallel resistors, we add the inverses and then we take the inverse of that. So it's going to be 1 over 60 plus 1 over 90, and then we have to take the inverse of that resistor as well. So resistor number 5, grab my calculator here. We have the inverse of 60, the inverse of 90. We get a decimal, and then you have to take that inverse as well, 36 ohms. And maybe I should actually stop and answer a question that some of you might have. Why, when you add parallel resistors, does the total resistance come out smaller than the individual resistors? Because that is always the case. The reason for that, here's an analogy for you. This chapter is all about analogies. There is, if you drive to Vancouver, between like Chilliwack and Vancouver, there is pretty much one highway. There is only one road. And that road, if you've driven on it, you probably have, it's busy, right? There is lots of traffic and it's slow. If they built a second road, that would be like adding a resistor in parallel, right? Parallel resistors is adding another pathway. So if they added another pathway, another resistor, another road between Chilliwack and Vancouver, would that make your commute easier or harder? And the answer is it would make it way easier, because now the traffic could divide itself up on both roads and there's less congestion. And what if you built a third pathway? What if you added in another resistor in parallel? Well, if you added a third pathway between Chilliwack and Vancouver, then it's even easier again, because now you can spread out all the traffic over 3 pathways. There's even less congestion. So every time you add a resistor in parallel, you're going to find that your total resistance actually goes down because you're reducing congestion. The coulombs have more space to move, more options, and it makes life easier. So anyways, back to the puzzle. My ADD is kicking in, right? Hey, look, there's a squirrel. Resistor 5 is worth 36 ohms. I have redrawn the picture for you with resistors 3 and 4 combined into resistor 5. We don't usually redraw the diagrams just because it takes too long. But since this is the first puzzle we're doing together, let's redraw it. We have resistor 5 worth 36 ohms. Now I want you to step back and look at this bottom picture and see if you can find some resistors maybe in parallel or maybe some resistors in series. And some of you are going to look at that and go, hey, what about these two? Well, there's two resistors in a line. There's no junction in between them. Those resistors are in series. So I'm going to give myself a little note here. We're going to add some series resistors. Let's take resistor 2 and resistor 5 and squish them, combine them into one resistor. We'll call it resistor 6. We'll just go with the next number in the number line. And remember to add series resistors. It's really, really easy. We just add them. So it's 24 plus 36. Resistor 6 is worth 60 ohms. Now we typically wouldn't resketch this, but again, because it's the first one we're doing together, I have resketched it for you. So let me scroll down. There we go. Resistor 6 we said was worth 60 ohms. So now we can look at those two and we can say, well, how are they related? Well, it looks to me like resistors 1 and resistor 6 are connected just by wire on their tops and just by wire on their bottoms. And that satisfies the requirements for parallel resistors. So these two are in parallel. I'm going to make a little note as to what I was doing with my number crunching. And now that we're combining these two resistors down into like one resistor, and that's the only resistor that's left, that's now the total. So once you get it down to like the last single resistor, you could call it 7 if you want. I'm just going to call it the total because we're down to like a single resistor. And the math says the inverse of that is equal to the inverse of 40 plus the inverse of 60. And if we throw that in our calculator, I know it's going to come out smaller than both 40 and 60. It's not that small, not the decimal. Got to take the inverse of that. 24 ohms. So it turns out all of those resistors that were sitting there initially have a combined resistance. Took us a few steps to get there. They've got a combined resistance of 24 ohms. So if I scroll back, we have found RT. Success, part A is done. Now what you're going to do next every time is find the total current. So if you look at this circuit now, we know that we've got a 48 volt battery. So we know the voltage. We know the total resistance is 24 ohms. We can simply head to Ohm's law. So we can run a quick Ohm's law calculation where we take the total current, or we're trying to find the total current. That's equal to the total voltage divided by the total resistance. I equals V over R. We're just using total values. That's all. So 48 over 24. We get a nice number. We get 2 amps of current. So we have 2 amps of current leaving the battery. That means we're also going to have 2 amps of current coming back to the battery. But there's going to be some splitting that happens along the way because there are some junctions. So we can say, hey, part B done. Got the total current. And now we have to find all the individual currents and voltage drops. So we're going to go back to the original circuit, not the weird sort of combined one. We're going to go back to this. And we have to find all the bits and pieces, I like to call it. So this is where we're going to use the tools in our toolbox. And you can't pick a tool. You have to use whatever tool sort of works for the job. We're going to use loops. We're going to use junctions. And we're going to use Ohm's law. Those 3 things will solve all the voltages and all the currents. So here's the first thing I would always ask yourself. We found that we had that total current of 2 amps. Coming off the battery. I like to go and label currents in here. I find it very helpful. You probably will as well. So we have 2 amps of current coming off that battery. I would always look to see or ask yourself, are there any resistors in this circuit that get the full 2 amps? And it actually turns out the answer is no, because there are 2 amps that come off the battery. I'm going up, but you could have gone down. It doesn't matter. There are 2 amps coming off the battery, but then it runs into a junction. And remember, what happens at a junction is current splits, but it splits somehow. I don't know how it's going to split in this case. It's not going to be 50-50 because the resistors are not the same in both pathways. So that 2 amps is going to split somehow. I do know that down here, that split current is going to come back together, and I'm going to be back to my full 2 amps at this point. But that doesn't help me find any of the other currents in the circuit. So I would always look to see if current will help you get started. Sometimes it will, sometimes it won't. It's like a 50-50. So junctions is not going to work for us to get started. So that means if junctions doesn't work, that means loops, it will work. And remember, loops was all about going on a shopping trip. And you have to spend all your money around a loop. So if you decide to go around this loop, I would maybe trace this with my finger, but you won't be able to see that, so I'm going to do it with a color. If I go around this loop, how many stores did I hit? Well, I only hit store number 1, resistor 1, which means I had to spend all my money. Kind of cool. I left with 48 bucks in my pocket, and I only hit 1 store. So I know that my spending habits at store number 1, they have to be, I'm going to switch to a nicer color to see, that has to be 48 volts. And I want to keep track of sort of what's going on here just so we can follow it. So I'm going to say, hey, I use loops here to figure out that V1 was 48 volts. I only hit 1 store, I got to spend all my cash. Now, once you know 2 out of the 3 pieces of information for a given resistor, you always want to find that 3rd one. So if I know the voltage and I know the resistance for resistor 1, then I should probably go and find the current. And to do that, I can just do a quick Ohm's law calculation. So now we can do Ohm's law. We know that I is equal to V over R. So I is equal to 48 over 40. Is that 1.2? Let me double check just in case. Yeah, 1.2 amps. So I know that I have 1.2 amps of current heading down through resistor 1. And I like to label those currents in there because hopefully by labeling that, I just opened up a door for you, something that you can see. We had 2 amps of current coming off that battery, and then we said it hit a junction, and we didn't know how it split. But now we know that we lose 1.2 amps of current down through resistor 1. So how much current is left rolling along the top? How much is left right there? Well, it's an easy subtraction, right? 2 minus 1.2, we're down to 0.80 amps left. And that 0.80 amps is going to turn the corner, and boom, it's going to run into resistor number 2. So it's actually kind of cool. We were able to now use a junction. I should make a note here as to the train of thought. We used junctions to figure out that there was 0.8 amps. So we had this 2 amps of current. We lost 1.2 amps down through resistor 1. And that left us with 0.8 amps. And that was equal to I2. So we used junctions there to figure out a current. Now we know a current and we know a resistance. Last thing to find for this resistor is voltage. Let's go get it with an Ohm's law. Always finish off those resistors if you can. If you take Ohm's law and you rearrange it, it's V equals I times R. So it's the 0.80 amps times 24. 0.8 times 24 equals 19.2 volts. Now notice in this circuit, I should probably step back here for a moment. Notice that we didn't just decide we wanted to go find all the currents, right? Notice we didn't decide we wanted to just go find all the voltages, because you can't just decide that you want to find stuff. You have to just sort of find what you can. So here's what you want to do, and here's the other little trick. The last thing that you find with Ohm's law is going to be the number that you need to find the next thing in the circuit. So we just discovered that we spent $19.20, 19.20 volts at store number 2. That means that voltage is going to help me figure out some other spending habits, and that's all about loops. So let's go, we already talked about this loop, right, where we hit one store and we spent all of our money. Let's go in another loop. What about if we go shopping and we go, I don't know, this way? Well, if we take that loop, we hit 2 stores, but the cool thing is we already know how much we spent at the first store. At store number 2, we spent $19.20. We have to spend $48 in total. So we can use loops and an easy little subtraction to figure out what our spending habits are at store number 3. So let's go back to loops. I know that my spending at store 3, I had 48 bucks in my pocket to spend. We spent $19.20 at the first store. I think that's 28.8. 48 minus 19.2. Yeah, we spent 28.8 V for volts at store number 3. And at this point, this is where my brain would go. Some of you are probably doing the same. You might be looking at that and going, hey, that number actually goes somewhere else too. Because not only is that a loop that I can take and spend some money, but what if we hit the last loop, which is this one, right through here? I have 48 bucks to spend. I still hit store 2, and then I just hit one more store. So hey, like the spending habit at store 4 has to be exactly the same as it was at store 3. So what's kind of cool is if you want, you could say, hey, loops also says that V4 is 28.8 volts. And those resistors, we said 3 and 4, right off the bat, we said they were in parallel. And you may recall that parallel resistors have equal voltage drops. So there's another little train of thought you could have used. It's kind of neat. Now what you've got is just Ohm's law times 2 to finish this thing off. Although I want to show you another option, because at this point we've actually got some options. I'm going to do an Ohm's law to figure out I3. I'll color code this so we can see what's going on here. I3 is equal to voltage 3 divided by resistor 3. 28.8 divided by 60 is 0.48. 0.48 amps. Done. Got resistor 3, and now we're like one current away from being finished. You could simply do another Ohm's law to find I4, or just to show you some other options, you had 0.8 amps of current coming down through resistor 2, and we just lost 0.48 amps off in this pathway. So you could, if you want, say, hey, let's use junctions, because there's a junction right there. You could use junctions to figure out I4 as well. And I'm going to do that just for kicks. So I'm going to use junctions. The math is easy. Junction says, hey, the current at 4 was the 0.8 amps coming in. It split. We lost 0.48 down through resistor 3. That's got to leave us with 0.32 amps left going through resistor 4. The rest of the current. And then the 0.48 and the 0.32 would combine back to 0.8 right there, which would join up with the 1.2 to take us all the way back to 2 amps. So there's a circuit puzzle. I think these things are awesome. I would do them in my spare time if I had a booklet of them. The homework that goes with today, I don't want you to worry about the questions from the textbook. I want you to try the resistor network assignment, which I'll pull up here in just 2 seconds. All right, hopefully you can see most of this on the screen. It might be chopping some of it off. But the homework I'd like you to try over the next couple of lessons is this, the resistor network assignment. I've got some sort of combo resistors here where it gives you the voltage and it tells you what each resistor is. I want you to find the total resistance, then find the total current, and then find all the individual voltages and currents. What you can do once you're done that is you can also find the total powers. Just do some P equals I times V. That's just something sort of an add-on there. Do your calculations like it says here on a separate piece of paper. And please make little notes as to whether you're using loops or junctions or ohms and how you combine resistors, like put a little series or parallel note. I maybe would say, based on that this first lesson, well, I guess second lesson with Kirchoffs, maybe try out the first three and see how those go. Now, some of you are going to find these puzzles click in your brain quite quickly, and other people they might not. So I would love for all of you, let's get a big group of us, I'd love for all of you to join me in our next Zoom meeting, and we'll chat about this. Because I'm happy to pull this thing up and we can like all talk together. And even if you think you know what's going on, just to hear us chat about sort of questions that people might have will be really beneficial to you. I'm happy to sit there and actually do some of the calculations with you and help you get all this sorted out. So I'd say maybe try the first three for practice. Although if you have fun with the first three, you could always try 4 and 5. I will give you a heads up that number 5 is very tricky to find the total resistance. So when you get to number 5, if you find RT, you might want to email me or ask me in a Zoom meeting if you've got the right total resistance before you go on to do the rest of it. And if you don't have the total resistance, we can chat about how to get that. So that's the homework. Again, don't worry about the textbook stuff that's listed with Kirchoffs. Just try these circuit puzzles. See if you can get a handle on that. And please join me in a Zoom meeting. Let's talk about this stuff and let's try some out together. Have fun, folks.